Okay, so we're picking up where we left off on lesson 39, and we're going to see how we can use radians to find the length of an arc on the Earth when we're talking about distances between cities that are very far apart and things like that. We're talking about a curved distance. We're not talking about a straight line because the Earth is curved, and so distances are really arc lengths. And so we're talking about latitude and longitude. The latitude of a point on Earth is the degree measure of the shortest arc from that point to the equator. Okay, so you can see that yellow arc there. The equator is the horizontal line that goes around the Earth, and or the horizontal circle that goes around the Earth. And so the shortest arc from the equator to, for example, the city of Los Angeles, that is the latitude, is the angle that's made when you go from the surface to the center of the Earth to whatever point on a certain circle of the globe that you're looking at. All right, so you're looking at this 34.05 degree angle up from the equator to a city like Los Angeles. And the question is, how far is it from Los Angeles to the equator if the diameter of the Earth is 7,920 miles? All right, so it's telling you that the diameter of the Earth is 7,920 miles, which means that the radius is going to be half of that, which is 3,960 miles. And then you have the that other ray on the angle that's going up to LA. And so what you're wanting to do is find that arc length, that yellow arc length. And up till now, the way you have found arc length is to think about it as a fraction of the total circumference of the circle. So when I'm looking at that arc length, I'm thinking, okay, well, the circumference of a circle is 2 pi r, and I'm dealing with just 34.05 degrees of the whole 360. So the way that you used to, or you still can actually find the length of the arc, is to use that method and say, okay, arc length is equal to the fraction of the circumference that we're talking about. So the fraction of the total circumference is right here, because all the way around is 360. So we're looking at just 34.05 of that 360. So that fractional part of the circumference, which is 2 pi r. And so you just fill in for r, we have 3,960 miles, and then you multiply that out, and that is 2,353.37 miles from the equator to LA, the shortest distance, and that's that arc length. Or another way to do this is to just convert degrees to radians to miles. All right, remember, a radian, when we're talking about a length, is just the length of the radius. That is a radian. Okay, that distance is 1 radian. 1 radian in this particular circle is 3,960 miles. So a radian is the length of a radius. When we're talking about an angle having a measure of 1 radian, we're talking about the measure of the angle that cuts an arc that has length 1 radian. All right, so we can just convert degrees to radians because we know how many degrees are in a radian, and we know how many radians are in a mile in this particular problem, 3,960 miles in 1 radian. So we can do this just like we would do unit multipliers. We're starting out with 34.05 degrees, and we're going to change degrees to radians by multiplying pi radians over 180 degrees. Remember, we talked about the fact that all the way around the circle is 2 pi radians, 2 pi r. All right, radian is a radius, the distance. All right, so 34.05 degrees times pi radians over 180 degrees, so I'm just saying half the circle is pi radians, since all the way around is 2 pi radians, and you could use the unit multiplier 2 pi radians over 360 if you want to. It's the same fraction. All right, so now the degrees cancel, bottom and top. Whoops, I canceled the wrong thing, but that's supposed to be canceling the degree measure there. I canceled the multiplication sign by accident, but anyway, you get what I mean. And now we're at radians, and so we can multiply by the unit multiplier that relates radians and miles. We know there's 3,960 miles in a radian in this particular circle. So we can multiply by the unit multiplier 3,960 miles over 1 radian, and the radians are going to cancel, and we're left with miles. So we just multiply 34.05 times pi times 3,960, and then we divide by 180, and we get the same answer we got before, but it's another way to think about it. We're just thinking about this now as just changing degrees to miles or whatever distance we're talking about using radians. We go through radians, we change degrees to radians, and then we change radians to a distance. And that's the good thing about radians, is that it gives you this connection between degree measure of an arc and the actual length of the arc. All right, and we can also use the same kind of thing when we want to measure the height of, say, a building or some really big thing from a long distance away, where we're not dealing with a right triangle, where we're maybe not on level ground and we're not close to the building, and we want to see how tall the building is. So maybe we're far, far away. And so we're wanting to measure the height of the building, and we do it by just using measuring the angle that we would see from the bottom of the building to the top of the building. So in this particular drawing, you can see it's 0.6 degrees, this angle we create from where we're standing way over here, top of the building, bottom of the building, and we kind of imagine this big circle. We're standing at the center, and the building is on the edge. And since we're 4,000 feet away, this is the length of the radius of the big circle that you could imagine, with us being at the center and the building being on the edge of the circle. Now, when we're dealing with angles of very small measure, like 0.6 degrees, the difference between the arc of the circle that is cutting and the actual straight line that is the height of that building is insignificant. I mean, they're almost the same thing. And so this method is sometimes used to measure the height of something really far away. You're actually finding the arc length, not the height of the building. But since they're so close together when you're dealing with a tiny angle like this, it's a good estimate of the height of whatever you're looking at. Okay, so we're going to, again, just use the same method of changing the degrees to feet this time, because we know that the radius of our circle is 4,000 feet. So 1 radian is 4,000 feet in this particular circle. So we start with 0.6 degrees, and we're going to change degrees to radians by the same unit multiplier we used last time, pi radians over 180 degrees. You could use 2 pi radians over 360 or pi over 2 radians over 90. I mean, it doesn't matter. This one's just easy to use. And so that will cancel the degrees. So now we're at radians, and to change radians to feet, we know there are 4,000 feet in 1 radian. So that unit multiplier will cancel the radians. And now we just multiply 0.6 times pi times 4,000 over 180, and that's about how tall the building is, 41.89 feet. That's actually the measure of the arc, like I said, but it's very close to what the building is, because this angle's so tiny. When you're dealing with a tiny angle, the arc and that straight line are very, very close. All right, moving on to forms of linear equations. You've probably seen these before. We like to use the slope-intercept form of a line, y equals mx plus b, to help us quickly see the slope, m, and the y-intercept, b, of a line. So that's pretty much our preferred way to think about the equation of a line, because it's easy to work with, and it's very useful for all kinds of different situations where we know different pieces of information about the line. So when I see y equals 2/3 x plus 5, I know that's a line because it's a linear equation. The highest power on x or y is 1. And I know that the slope is 2/5 because that's the coefficient of x, that's m. And I know that the y-intercept is 5 because the constant b is 5. There are other forms of the equation of a line that help us to see other characteristics of the line. And you need to be aware of these different ways to write the equation of a line. And you just need to be able to change any equation you have into these different forms. All right, so the general form of a line is ax plus by plus c equals 0, where a, b, and c are integers. All right, so sometimes we want to write the equation of a line in this form. We want to make sure that the coefficients of x and y are integers and the constant is an integer and that everything is on one side of the equation. So you need to be able to manipulate any equation of a line to get it into this form. And to do that, all you have to do is multiply, first of all, to get rid of any fractions there might be. So in this problem, y equals negative 7/3 x plus 1/5, we would want to multiply the whole equation through by 15 so that we wouldn't have any fractions left. So 15 times that whole equation, the 3 cancels and we end up with negative 35x, and then the 5 cancels and we end up with 3 for the constant. So we've gotten rid of all the fractions now, and we want to move everything to the left side of the equal sign in the order x term, y term, constant. So we want the x term to be first, the y term to be second, and the constant to be last. And then we want it all to equal 0. And probably, I'm not exactly sure, but in the back of the book they may expect you to write plus negative 3 instead of minus 3 for this part of it, just because in the general form both of the signs are plus. So they may push it a little further and expect you to write this as 35x plus 15y plus negative 3, and that's fine. All right, so that's the general form of a linear equation. Another form that you'll see sometimes is the double intercept form. This form allows you to see the x and y intercepts of the line really quickly, because if you put your line in this form, that denominator for the x fraction is your x-intercept, and the denominator of the y fraction is your y-intercept for that line. So if you have an equation like 2x minus 3y plus 4 equals 0, and you want to put it in double intercept form, the way you're going to do that, first of all, is to arrange the equation so that the x and y terms are on the left and the constant is on the right. So you're going to move that 4 over to the right, and you'll have 2x minus 3y equals negative 4. Then you want to divide the whole thing, the whole equation, by the constant, negative 4, so that you'll get 1 on the right side. So you divide everything through by negative 4, and then you'll have 1 on the right side. So I just reduced it and separated the two fractions also at the same time. So 2x over negative 4 would be negative 1/2 x, and then negative 3y over negative 4 would be positive 3/4 y. All right, you're almost done. Now you want to rearrange the left side so that you have two fractions with just x and just y in the numerator, respectively, and with a plus sign between them. All right, because that's the only way you're going to really be able to look at the denominators and know for sure that the one under the x is the x-intercept and the one under the y is the y-intercept. So you have to get it so that you just have x on top of the first fraction and y on top of the second fraction, and then and you also have a plus sign between them. So you're going to just rearrange it. You're going to rewrite it so that you have, instead of negative 1/2 x, you're going to write that as x over negative 2. Means the same thing. And then you've got 3/4 times y, and that is the same thing as y divided by 4/3. So when you move that 3/4 down into the denominator, you have to flip it upside down, or it doesn't mean the same thing. So y divided by 4/3 means the same thing as 3/4 times y. And now you're done. You've got it in that form, and you'll be able to see that the x-intercept for that line is negative 2, and the y-intercept for that line is 4/3. All right, you also have the point slope form, which can help you to see a point on the line and the slope. So you might use this form if you were given a problem like the following. Find the equation of the line whose slope is negative 1/3 and that passes through negative 2, 5. So you can fill into this equation. You fill in the point with x1, y1, that goes in there, and then m is the slope. So in this point, they've given me my y coordinate is 5, so I'm going to put y minus 5 for y minus y1. And then my m is my slope. That's negative 1/3, so I'm putting that where m is. And then x minus x1 is going to be x minus the x they gave me, which is negative 2. And then I just rearrange, use algebraic manipulation, use the distributive property, all the things you need to do to get it into whatever form the question might ask you to leave it in. But you can actually do that same problem just using the slope intercept form, y equals mx plus b. So it's not necessary to use this form. It's just a form that it's good to know. I don't ever use it, but it's a good thing to know. And then the 2-point form is the last one, and this looks exactly like the point slope form, except instead of m, they're just putting the slope formula in the place of it, y2 minus y1 over x2 minus x1. So it's pretty much almost exactly the same as the point slope form.